My name is Tom Portuguese, and this is my presentation of Morphozoic, which is an abstraction of morphogenetic fields in a cellular automaton. So the objectives of this project are to devise an abstraction that models morphogenesis in a cellular automaton using a scheme called nested neighborhoods approach. So neighborhoods provide a very cellular automaton neighborhood provide a very straightforward representation of local and global fields. Local is essentially a smaller neighborhood, and global is a larger neighborhood. And it allows us to explore the idea of how local versus global information can combine to achieve morphogenesis. So what we're trying to do here is to embody a scheme that is computationally feasible. So each cell has a limited information processing capacity, which is, a plausible sort of assumption. Information about more local cell neighborhoods having fewer cells is more precise and finer grained than information about a larger, more global neighborhood. And this is simply because we're going to allocate a fixed number of bits to each neighborhood. So a smaller neighborhood is going to be represented proportionally by more bits. So, or a higher proportion of the neighborhood's bits will be represented. So, some definitions. A cell, this is a typical cellular automaton concept, possesses a state, which is going to be also used, we will also call it a type in this project. A cell will be able to emit, sense, and react to signals from other cells. So signals will carry information about the state of neighborhood cells. A field is a confluence of signals sensed by each cell. Requirements. We want this to be a compact. It's very important that we have a compact representation. We don't want to have a sort of geometrically or combinatorial explosion of information happening. We want to have some noise tolerance. So we want that because nature tends to be to build things that are noise tolerant, and these are actually this is actually a bit of a challenge for a cellular automaton. They typically aren't noise tolerant. We want it to be able to generalize, so we don't have to have a specific rule for every single thing we do. We want to be able to give a sort of set of exemplar rules, and then it can interpolate and extrapolate from those rules. And we will demonstrate that. And we want it to be able to be evolvable by some kind of counterpart of natural processes. If it's going to represent a morphogenesis even in some abstract way, and it isn't evolvable, it's quite a stretch to actually say that. So a cellular automaton, just to recap here, is in this case, it's a two-dimensional grid. Well, that's the typical case. Grid of cells. Cells have state value. We've given that already. And we're going to call that a type in Morphozoic. And each cell can sense the presence of nearby cells, typically a 3x3 Moore neighborhood. And nested neighborhoods are larger than that. And the cell states in a cell's neighborhood and a set of rules determine how the cell state changes. So it's a little bit like a Turing machine in that sense. So a morphogen, we're grabbing and co-opting a couple of names from biology, and in Morphozoic, a morphogen is going to be a morphogenetic field modeled as a set of nested neighborhoods in a cellular automaton. So a cell is a cell itself, we will call a zero neighborhood entity. A non-elementary neighborhood consists of neighborhoods of cells that are built around smaller neighborhoods. So neighborhood sub I is an n by n quantity of neighborhoods of the next smaller I sub I set. A morphogen is defined as a set of nested neighborhoods, and here's the definition. We have a picture later to illustrate that. A morphogen, I've coined the term sector, meaning one of the pieces of a neighborhood. So for example, a 3x3 neighborhood has 9 sectors. And so what we're going to do is the trick here that we're going to do to get hold of the and quantify the information in a neighborhood is we're going to represent it, each sector, by a vector of which is a histogram of the cell type densities contained within it. So that will actually allow us to have a fixed number of bits dedicated to each sector, hence a fixed number of bits dedicated to each neighborhood. Picture coming up to show this. Here's the picture. So here on the left, we have a grid, a cellular automaton grid with a very coarse representation of a gastrulation event. So if you had this, if these cells here were had this sort of indentation, and this kind of, and we'll show you how this actually develops. But given that it actually did this, here's some neighborhoods. So here's a neighborhood here. This is neighborhood sub 0, that one cell. Here is neighborhood sub 1, which is a 3x3 in this case. And here's a 3x3 of smaller, this is neighborhood sub 2, which contains 9 sectors, each of which is in neighborhood sub 1 entity. Down here we have the cell type densities. So this is actually the numeric representation for each neighborhood. So you can see the little bar thingies in here. That's the histogram. So it tells you how much of each type of cell. You have a specific number of types of cells we're going to allow. So over here on the bottom right, you see the histogram for this larger entity. So you can see the cell type densities that are in each one of these sectors above here. So a morphogen actually represents a pattern that you match on. So what you do with the pattern is you have to have some action. So the morphogen and an action combined together is another term pirated from biology. We call it a metamorph. So and we have so a metamorph will actually match on something and then accomplish a change once it matches. So the aspects of a metamorph are you have to generate them somehow. You have to create these things, and the execution of them is when you actually you operate on the things that you've captured or learned. So to generate them, there's lots of ways you can do it, but For some of the examples, the applications, we just kind of hand-coded, like that gas relation one was a hand-coded morphogenesis, and when it ran, we built up a set of metamorphs that represent that. There's other ways. For example, we'll see the game of life, and there's other ways to do it too. So the game of life, we're going to use the game of life rules. And when we execute a metamorph, once we match on it, well, the way we're going to match on it is using a distance metric. We're going to actually take our database of metamorphs that we learned, and then we're going to compare it against the morphogens that we actually that actually exist in a pattern. So those might not be exact matches to the ones we learned. Hence, we have a distance metric. Basically, it's a sum of a sum of a sum of the cell type density differences. And we come up with some metric to tell us how close we are. That's kind of rough. There's also a neural network representation that doesn't quite do it that discreetly, but we'll see that. So what we do is we match on that, and the one that's closest, we actually apply the rule that's the action that's associated with the metamorph. So one interesting thing that we've done in this project is to capture the metamorphs and package them up into an artificial neural network. So we can throw away the big database of lots and lots of metamorphs and teach a neural network in a very compact form how to match on the morphogens contained in the metamorphs and to output the actions that the metamorphs contain. So, and this is faster. This is very fast. You don't have to look stuff up. You just run a bunch of numbers through, some mathematical functions. There are far fewer elements involved, so it's compact, and it's more noise tolerant because artificial neural networks are quite well known as being noise reducing systems. So here's a picture of one. So what we're going to do is input the set of metamorphs that we learned and train a neural network, and then throw away or at least not use the metamorphs anymore. And the output will be the cell type. So metamorphs actually tell a cell how to change into some cell type. Okay, so now we have four applications that we've done for this project that we'll be showcasing. So the first one is Conway's Game of Life, which is a famous cellular automaton. So it's always good to kind of benchmark things that people know about. The next one we're going to do is show as an evolution of the simple gas relation sequence. The next one is to highlight generalization using the neural network implementation in a neuron pathfinding demo. Lastly, yet again, we want to compare this to things that are in the field, well-known system things that have been done in morphogenesis, and Turing's 1951 paper is certainly a landmark paper, which is the reaction diffusion morphogenesis. So Conway's Game of Life is a very simple, has four very simple rules. You have cells that are alive, cells that are dead. So the live ones are dark. In this case, the white ones are dead. And depending on the number, it just counts the number of neighbors that each cell has. And depending upon, so let's, for example, the first one, any live cell with fewer than 2 live cells as neighbors dies. And it's like, it's supposed to be an underpopulation thing. And you can see the other things. And you get some fascinating things that dynamic sorts of things that happen. One of which is a thing called a glider and a glider gun, which are like self-sustaining, oscillating, repeating patterns. So doing the game of life demonstrates the ability to reverse engineer a well-known set of cellular automaton rules. So at this point, I want to actually switch over to a little demo here. So, and what we're going to do is go over to this one and see if we can get it here. Not that one. Okay. So we're going to start up Morphozoic with the Game of Life application. And we're going to we're going to execute a previously learned set of metamorphs. And so I hope you can see this. Okay, maybe you can't. Are you actually seeing this? That's the question. No, you're not. So I'm going to have to share this little gizmo here. We're going to share this one. Okay, here we go. So the pattern you see here is a thing called a glider. So it actually is a self-sustaining pattern, and it moves across the grid. So this is what I'm going to do here is just step it along. And you might notice that it repeated. So it changes into 4 different things, and then it repeats, and it's moving. So this is not actually using the Game of Life rules. This is using the Game of Life rules that were learned by Morphozoic upon being exposed to this little guy as it was running the real Game of Life rules. Okay, so let's go back to let's go back to this thing and go on to the next application. And this is a gastrulation evolution. So before we evolve it, let's actually look at the gastrulation itself to see what we're evolving. So let me see. Okay, but this is going to demonstrate that the model is mutable and evolvable. So let's first look at what the gastrulation does as it evolves. I mean, not evolves, but when you run it. So let me share that when it pops up here. So we're going to share this thing. Okay, so it's a blank grid right now. So what we've got, we're going to step it. So first we see a single cell appear. So this is going to build into a set of cells. So here you have sort of a pseudo embryo developing, just a square. And at some point, it decides to indent, and that's the gastrulation. So this is actually running, again, with the rules that were learned by hand. When this was kind of hand programmed, Morphozoic learned the rules, and it actually it's running now. So, and one of the things it gives you is a little bit. You can see. I'll illustrate some of the. If I kind of fuzz this up a bit and make it sort of damage it a bit, you can see. I hope I didn't damage it too much. Okay, maybe. Oh, is that one went away too? Okay, so it has some repairing things here, qualities. So the rules actually will force it to repair it and get it into a state that it knows. So that's the that you wouldn't find with your typical cellular automaton. However, if I put something over here, some extra stuff, we'll go into. Let's just see. It sort of forms a tumor because it doesn't know how to fix it. So now it's kind of off the rails because it thinks it's another cell thing, and it's trying to evolve that. It's trying to build that into something, but it's not going to be anything. So the repair works to an extent, but it can't repair everything. At some point, it's overwhelmed by something that it can't fix, which is a very interesting thing to investigate in itself. So now what I want to do is cut out the screen share again. Go back. Let me set up something else here. Okay, let me share this. And I'm just going to show you the very beginning of the evolution of that cell morphogenesis. And it has to initialize for a bit. And you'll start seeing it'll start to. So the evolution is actually a genetic algorithm. So it actually has a fitness. It has a population of essentially guesses, and it starts to it rewards better guesses, and it keeps those in the population, and it mutates and crosses fit members, and away it goes, trying to build the very first cell division into that sort of the smallest box. So you can see it's sort of trying to do that. And so it'll go on and on for a number of hours actually, and so we won't let it do that. But at the very end, what we've got, if we go back to the slides, is go back up here a bit. You can see on the right side, it actually gets, after hours of running, it actually is able to evolve that pattern, which is quite a challenge actually. So it actually suggests that it is an evolvable, Morphozoic is an evolvable model. So moving along, this is neuron pathfinding, which is something that happens in the brain where one neuron sends out an axon to try and find other neurons, and there's some signal being emanated by target neurons to cause the axons from the source neurons to seek out the targets and connect to them with the synapse. So I do not have an actual demo of this, but because it takes quite a bit, this one uses the neural network. Neural network is very valuable for this because of the generalization. But it so we generate metamorphs from a bunch of random configurations of source and target neurons, and then we train them. We train an artificial neural network from those, and then we supply a novel pattern that it hasn't been trained on. So, and it will actually be able to generalize on the learning that it used, that it acquired from the previous learning. Okay, lastly, we want to do Turing's reaction diffusion morphogenesis. So, in a cellular automaton, what we're going to do is kind of discretely map a bunch of values to cells randomly. Turing's reaction diffusion has a set of a dual set of differential equations. Well, it has two quantities that dynamically interact with each other through a couple of equations. So if you set a couple of parameter constants, it will produce a number of different patterns. The pattern I selected here is the so-called, sometimes called the cheetah pattern. It looks like a cheetah coat, sort of. So after a while, I'll show you how this actually starts up and gets to that point. So what we want to do is try to get the Morphozoic to see if it could actually watch the Turing diffusion reaction thing and see if it could actually produce something from learning from that. So here's what it did on the right. It's not as nice and pretty, but it is definitely a discernible pattern, cheetah pattern. And it uses the artificial neural network once again to smooth things out, which is quite useful, quite handy. So let's switch over and just check out. We got one more little demo here to show. And what we're going to do is, okay, let me actually which one is this? Show, there's that one, the Pathfinder. Oh, here it is. Okay. So here I'm going to run it. I'm not seeing it here. All right, let's just see if we can do this. All right, this will work. Let me share this. So you got that. Okay. All right, so here we have, and now we're going to step it. So the first step is the random pattern, and now so this is not Morphozoic. This is actually the Turing equations doing this. So step, and you can see it forming the pattern fairly rapidly. So there it is. Now I'm not going to show you Morphozoic doing this because it takes a long time to train this. Training the neural network. I could have actually saved the neural network and read it back in, but I didn't do that. So, but you saw the result in the paper there. So that is the my presentation of Morphozoic. So thank you.